Hi, and welcome to part 2 of our MOSFET fundamentals training. So, what is a MOSFET? In part 1, we learned that a MOSFET is a three-terminal semiconductor typically used as a solid-state switch. MOSFET stands for metal oxide semiconductor field effect transistor, and it has three terminals, which are the gate, the drain, and the source. The drain and the source are the switch terminals, and the gate is the control pin that turns on and off the switch. Unlike electromechanical switches, which use springs and mechanical contacts to operate, a solid-state switch has no moving parts, but instead uses the electrical properties of solid-state semiconductors to perform its switching functions. In this part 2, we are going to focus on N-channel enhancement mode MOSFETs, which are the most commonly used type of transistors. More specifically, we will go over several parameters affecting MOSFET use, namely maximum operating temperature, heat generation, and heat dissipation. Stay tuned. Let's start by taking a look at the maximum operating temperature of MOSFETs. Many times, when discussing MOSFETs, you will see the maximum operating temperature mentioned as a parameter of high importance. But why is that? Well, first of all, the maximum operating temperature of a MOSFET affects three very important aspects: the MOSFET's efficiency, its maximum current capability, and its reliability. Let's start with efficiency. When the MOSFET operates by turning on and off, it loses some energy in the form of heat. The more energy it loses, the more it heats up. Heating up is not an intended function of the MOSFET. This means that the less it heats up, the more efficient it is. Using a cell phone as an analogy, an electronic system is more efficient when the energy used to operate the device supports the intended functionality of the system rather than being unnecessarily wasted as heat. When a cell phone operates, it uses energy from the battery to perform the communication features that it was designed to do. However, it also heats up. Heating up is not the intended function of the cell phone either, but rather a manifestation of the losses presented in the form of heat. Some of the battery's energy is wasted as heat while it is operating. The battery will last less time due to these losses. So these losses in the form of heat define the efficiency of that system. The lower the losses, the higher the efficiency, meaning less energy is lost to heat and more energy goes to the communication functionality of the cell phone. Similarly, a MOSFET that enables the switching features it was designed to do with the least amount of heat dissipation is more efficient. Another parameter that is significantly affected by the operating MOSFET temperature is its maximum current capability. The MOSFET's maximum current capability is a function of its efficiency and the system's ability to remove the heat that is generated by the MOSFET when it is conducting and switching this current. This means that if you operate the MOSFET at lower temperatures, you can increase the current it can drive. This current capability is directly related to the product's power output. For instance, a cell phone charger with a higher current specification can deliver higher power, thus charging your cell phone faster. The last parameter is the MOSFET's reliability. Operating the MOSFET at higher temperatures decreases the probability that the MOSFET will perform its intended function over the planned lifetime of the product. In other words, a MOSFET working at higher temperatures might work for a shorter period. This does not necessarily mean that it will fail, although this is a possibility. A more reliable MOSFET will operate in a defined environment without a failure. As a final remark, please note that the maximum MOSFET temperature is typically 150 degrees Celsius or 175 degrees Celsius and should never be exceeded. Now we know that keeping the MOSFET operating at a relatively low temperature is critical to enable best performance. But how can you do that? It depends on two parameters: power losses and thermal resistance. The power losses, which are basically the sum of conduction and switching losses, lead to the generation of heat, in other words, how much the MOSFET heats up. The thermal resistance, on the other hand, leads to the dissipation of that heat, which means it will depend on how much heat the MOSFET can dissipate. To conclude, if your MOSFET is generating a lot of heat and having high power losses, you will need to find a solution to dissipate it, which means having a lower thermal resistance and vice versa. Simple, right? Let's explore further by taking a look at heat generation. Let's take a look into how MOSFET losses originate, causing it to heat up when operating. A MOSFET is a solid-state switch controlled by a voltage applied at the gate. This signal at the gate will turn on and off the switch. The goal of turning on a switch is to allow current to flow through the switch's terminals. So, what are the losses that may happen during the MOSFET operation where heat is generated? Conduction losses happen when the MOSFET switch is turned on and current flows through the MOSFET. Alternatively, switching losses happen when the MOSFET is transitioning from being switched off to being switched on, and vice versa. As new electronic devices aim to offer higher power output to consumers, these higher power levels result in higher currents flowing through the MOSFET, which also generates higher amounts of heat. So, new MOSFET technologies need to offer lower conduction and switching losses with higher levels of current driven by the MOSFETs. Let's now learn more about these conduction and switching losses. First, let's introduce some parameters that are important for your understanding of heat generation in MOSFETs. RDS on represents the conduction losses and it stands for drain source on resistance. It is the MOSFET's electrical resistance when it is turned on. Regarding switching losses, there are several parameters in the MOSFET specification used to calculate them in a specific application. We are going to focus on two critical ones for simplification, as they provide a good representation of the overall switching losses in a MOSFET. They are the QG, or gate charge. The gate charge is the amount of charge needed to turn on the MOSFET. Transistor parasitic capacitances are a significant factor in determining the energy that will be lost in the device during a transition from on to off state or from off to on state. The capacitance, or C, determines the amount of charge, or Q, that needs to be supplied to or removed from various terminals of the device to change the voltage across these terminals. The faster this charge is supplied and removed, the faster the device will change voltage and will turn on or off. As you can see, the MOSFET has many associated parasitic capacitances. The signal applied at the gate will start providing charge until the input capacitances, CGS and CGD, reach a certain voltage value where the MOSFET will fully conduct current through the drain and source terminals at the lowest RDS on level achievable by the MOSFET. The lower the MOSFET's charge requirements, the smaller the switching losses, and the faster the MOSFET can be switched on and off, and vice versa. The charge applied at the gate is typically provided by a gate driver or directly from a logic-level device like a microcontroller. If you want to turn on and off the MOSFET faster, in other words, at higher frequencies, the gate driver needs to supply this charge at a faster pace, which requires higher current levels supplied by the gate driver. Another critical parameter in the MOSFET specification is the QoSS, or output charge. Both parameters, QG and QoSS, are the associated input and output charges of the MOSFET, which will be explained in more detail next. So, as we have seen, it is crucial to reduce the RDS on, QG, and QoSS to decrease the power losses and consequent heat generation. That mainly depends on the semiconductor technology you use. Infineon's trench MOSFET technology evolution has continuously improved by consistently decreasing the RDS on per area for each technology node in Infineon's Optimus MOSFET technology, as you can see on the graph. This means that, even though the die area of the MOSFETs has been reduced, Infineon has been able to lower conduction losses as well. Likewise, you can see on this graph that the switching parameters QG and QoSS, represented as a figure of merit product, have also been decreasing significantly with every technology step. So, the R&D teams at Infineon have been successful in lowering both conduction and switching losses with every technology step. However, there is always a compromise in the development of new MOSFET technologies. When you optimize for conduction losses, you sacrifice switching losses and vice versa. For instance, when you are selecting MOSFETs from a particular technology like Optimos 5, as you go lower in RDS(on) in your selection, you should expect to see a higher gate charge (QG) specification. Another thing to consider is the die size. The die is the piece of material, the silicon, that is inside the MOSFET. In this particular example, you can see two Optimos 5 MOSFETs. The one with the lower RDS(on) value of 2.7 milliohms has much higher QG and QoSS values than the Optimos 5 device with the higher RDS(on) value of 5.2 milliohms. However, you can see that the one with the lower RDS(on) has a bigger die size. In short, in terms of choosing a MOSFET, Infineon offers a wide range of improved technology from which you can make your selection according to your very specific needs. Now that we understand how heat is generated when a MOSFET is operating, let's explore how that heat can be removed, or in other words, dissipated. Heat dissipation is important because, even though new MOSFET technologies generate less heat, they still have losses. If we don't remove this heat, the temperature will start rising in the MOSFET. Eventually, the MOSFET will reach its maximum allowed temperature, which could lead to performance issues and, if the temperature becomes too high, catastrophic consequences such as complete failure of the MOSFET. To display this, let's look at two identical MOSFETs that are driving the exact same current. As you can see, the MOSFET on the right with the smaller heatsink assembly cannot get rid of the heat fast enough, and its temperature rises higher. To understand heat dissipation better, let's talk about thermal resistance. Thermal resistance is a measure of the ability of a material to block heat flow. Let's use an analogy. This white ceramic cup has a higher thermal resistance, blocking the heat flow and, therefore, keeping the coffee hotter for a longer time. The ceramic material's ability to block the heat from dissipating into the air defines its higher thermal resistance compared to the glass material, which allows the coffee to cool off faster, thus having a lower thermal resistance. In summary, a high thermal resistance means the object does not conduct heat well, and a low thermal resistance means the object does conduct heat well. And since with MOSFETs we want to remove heat, a low thermal resistance is better than a high one. You may now be wondering, but how can I lower the thermal resistance of the MOSFET mechanical assembly? So, the power consumed in a MOSFET when it is conducting and switching is dissipated in the form of heat to its surrounding environment while it is operating. This dissipation is partly performed through packaging technologies and the PCB assembly heat sinking mechanism. Basically, when the MOSFET is placed on a plate, the PCB and heatsink will contribute to the heat dissipation since the heat will leave the MOSFET and be transferred to them. So you can achieve effective heat extraction or heat dissipation by physically attaching the MOSFET to a material with a big mass that is a good heat conductor. If this is not the case, the MOSFET will heat more, which may lead to reduced efficiency, maximum current capability, and reliability, as previously mentioned. For this reason, the more heat that is generated, the more efficient the heat sinking mechanism needs to be, or, in other words, the lower its thermal resistance needs to be. This thermal resistance from the semiconductor junction to the ambient air is called junction to ambient thermal resistance. The junction to ambient resistance includes the whole path the heat will follow from the MOSFET die, where the heat is generated, all the way through the MOSFET package, PCB glass, its thermal vias, and the heatsink, until it is released to the ambient. Here, we have a comparison between a 3x3 MOSFET and a 5x6 MOSFET in terms of heat dissipation. If it is not sufficiently wide, the footprint area can become a bottleneck for heat flow going from the MOSFET to the heat sinking element. Similar to what we learned when we discussed heat dissipation, the heat from a smaller package, here the 3x3 PQFN, will have less access to the heatsink than a 5x6 PQFN package, for example. This is why the packaging is so crucial for the heat dissipation. So, what can Infineon offer in terms of packaging technologies? This graph shows the calculated total thermal resistance junction to ambient of different MOSFET packages using the same PCB heat sinking mechanism versus their footprint area. For example, the S-Toll package has a similar heat dissipation capability to the DPAC package at about 10 kelvins per watt. However, S-Toll has a smaller footprint with 47 square millimeters and DPAC with 66 square millimeters. Thus, S-Toll in this comparison against DPAC requires less space on the PCB and could be a good option for a middle ground MOSFET. Please note that this graph does not show the different packages' thermal resistances. Most modern power packages used with MOSFETs are already below 1 kilowatt of thermal resistance, and a better representation of their thermal performance is by assembling them on a PCB with a heat-sinking mechanism. However, depending on your needs, you may prefer high thermal resistance in exchange for a small size, for example. This is why you should select the MOSFET from Infineon's wide portfolio that best satisfies your needs, keeping in mind that a compromise will always occur. Let's take a look at a practical example. Someone designing small factor laptop chargers is asking for our MOSFETs for the load switch section of the design. Here is a simplified circuit showing the N-channel MOSFET, circled in green, that will be used as a load switch on the secondary side of the charger. We also have the technical requirements. Since space is highly constrained, we must choose a small PQFN package, although we need to consider the relatively high current specification of 4 amperes with a thermal resistance defined according to the PCB specification given to us. Based on these requirements, we can calculate the targeted RDS(on) value as follows. First, let's calculate the MOSFET's power dissipation. Since space is very constrained in this compact laptop charger, we should target a package that has a small form factor like PQFN 2x2. We know its approximate junction to ambient thermal resistance based on the specifications provided for the cooling mechanism through the PCB, which is about 60 degrees Celsius per watt. Based on the formula we previously introduced, we know that the temperature rise of the MOSFET is defined by multiplying the power losses by the thermal resistance. If we solve for power dissipation and introduce the ambient temperature of 60 degrees specified in the requirements, along with a maximum operating MOSFET temperature of 90 degrees Celsius, we can calculate the power dissipated by using this formula. Now that we know we will be dissipating 0.5 watts, we can calculate the target RDS(on) based on the current requirement of 4 amperes with the following formula, as there will be mostly conduction losses for this load switch. We also need to derate this calculated value by about 35%, since we will be operating at a high junction temperature at about 90 degrees Celsius as per the requirement, so the MOSFET should have an RDS(on) of approximately 23 milliohms. Thus, a very good match is PN ISK036N03LM5, a 30-volt, 3.6 milliohms power MOSFET. Now that we have learned about all the different parameters, let's put it all together. So, we have learned that the MOSFET's maximum operating temperature is the most critical parameter to take into account when designing and selecting a MOSFET. The temperature increase of a MOSFET is defined by 2 parameters. The heat generation, which is constituted of the power losses, the sum of the conduction losses and the switching losses, and the heat dissipation, which is related to the thermal resistance. The multiplication of these 2 parameters will result in the temperature increase in the MOSFET. The heat generation can be reduced by the semiconductor technology chosen, while the heat dissipation can be adjusted by choosing different packaging technologies. We also saw that new applications demand higher power output, thus higher current levels driven by MOSFETs, increasing their heat generation. To keep up with these higher current requirements, you can lower the losses in the MOSFET with newer silicon technologies, and improve the heat sinking system by using innovative packaging MOSFET solutions. Lastly, we learned that whenever selecting or designing a MOSFET, there is always a compromise, so you should identify the most important aspects of what you need. You have now finished the second part of this training about MOSFET fundamentals. If you need further assistance on this topic or would like to know more about Infineon's comprehensive power MOSFETs offering, please visit our webpage. Thank you for joining.